Hello, everyone.
Before you start, I have the pleasure to present the Integrated Information System concerning the multi-layer management of data of the rehabilitation of the Holy Aedicule. This is collective work within a project now, Expect. The PhD candidate Manolis Alexakis is going to present it. And the whole team is Associate Professor Kyriazis from the University of Piraeus, Associate Professor Anastasios Doulamis from NTUA, Dr. Kyriakos Lampropoulos, and me. Manolis, you are having the floor.
Thank you, Professor Moropoulou. We are going to see the information, the integrated information system that we have is still under development, but has been developed to a certain point so far. So an outline of this presentation, why it doesn't change, how do I go to the next slide? Okay. An outline of this presentation. In the beginning, I will introduce you to the analytic platforms, what we have so far, what we had in the past, and what it is existed nowadays, and introduce you to the analytic strategy that we follow to deal with this kind of problems, data management. And show you the progression of how analytic platforms have been evolved through time. Then I will give you a short introduction to the platform that we have developed, the one that we use in the project of the rehabilitation of the Holy Aedicule, where I will present you the main architecture, the architecture of the so far architecture. This is the first stage. This is going to be evolved and include more aspects in this architecture, the main utilities and the functionalities that we have already. Firstly, let's see some definitions of what analytics is. According to Wikipedia, analytics is the systematic computational analysis of data or statistics. It is used for the discovery, interpretation, and communication of meaningful patterns in data. It also entails applying data patterns toward effective decision-making. It can be valuable in areas rich with recorded information. Analytics relies on the simultaneous application of statistics, computer programming, and operations research to quantify performance. According to Technopedia, it's a similar definition, but it's more technical. Analytics is a scientific process. It's a scientific process of discovering and communicating the meaningful patterns within which can be found in data. It is concerned with turning raw data into insight for making better decisions. Analytics relies on the application of statistics, computers, programming, and operations research in order to quantify and gain insight to the meanings of data. It is especially useful in areas which record a lot of data or information. This is the case. The rehabilitation of the Holy Aedicule of the Holy Sepulchre in Jerusalem was a similar case study where a lot of different data, multi-dimensional data exist, and we have to find a way to cope with them and manage them efficiently. So let's start with the main analytic strategy that is usually followed in this kind of problems. For instance, an organization or an institute or whatever, the one that has a problem to resolve, is about how it's people of this organization, this university that we are. It's people, students, researchers, professors, processes, which tool they use, and the data that work together to collect, store, and analyze the data that they have collected. The first element is the people, the researchers, the individuals. explore when, where, and how people engage with data and analytics. Intelligent collaboration, it's critical to raise agility, let's say, to make it more easy to find a strategy to cope with the problem. Any discussion about data doesn't go far without reference to the data scientist. Always there has to be a data scientist to deal with this data and give us insights of them. But also there are many other critical roles needed to foster a successful analytic strategy, like probably data analysts, data engineers, or a business leader, the one that eventually a kind of manager. The second element is processes, which refers to how analytics are produced, consumed, and maintained, let's say. A modern approach to analytics is to support graded agility to be able to utilize scaling of data, let's say. So that requires faster data preparation from a wider variety of sources, rapid prototyping, and analytics model building and cross-team collaboration processes. The third key element of the strategy is the tools and the technologies that we use. In fact, it's the raw programs, the code that we write, let's say, develop, and applications used to prepare for and perform the analysis, such as the provisioning, flow, and automation of tasks, let's say, and the resources. As an analytical strategy gets mature, let's say, the technologies used to implement tends to move from archaic structures, let's say, the one started to develop since the 90s, to the ones that have come today, which is structures to composable microservices, let's say. We will see all of those in the coming slides. So starting in the 90s and during and through the mid 2000s, let's say the available data, it was mostly transactional data, and they were managed in a unified system. Often they were stored in a warehouse, in a data warehouse. So there, limited end users, there was the ability of the end users was limited. They could interact directly with the data, but there was severe technical and governance requirements. So it was very, you had to have an expertise to interact directly with those data. Let's see one by one those four key elements of the strategy presented before, and how they interact with these platforms by then. So IT professionals needed to kick off any data-based work by extracting data from a centralized, difficult to use source, as we said before. So because you needed expertise to interact with the system. This process could take days, and if someone needed to make a query, a request to get some data, to access the data, could easily exceed the IT team ability to fulfill those requests. Another problem was that if a change was needed to be done in the data collection or in the storage methods, it could easily take the IT team months to perform these changes. The data analysis and modeling work could take nearly as long. And experts did have some access to data through the so-called self-service business intelligence features. However, due to the same speed and accessibility issues that they also had, they faced, it was often difficult for the domain experts to lead with the data for decision making. Now, with regards to the processes, IT professionals gathered requirements for analytical projects before they could build or deploy a solution, deploy a model, let's say. They classify the sources of data that they used, and data probably coming from external sources. As part of the warehousing process for all of this data, it was decided which of those data sources to store and how to store them. Each time it has to be a decision for each different data set. Also, and most important, once deployed, data passed into the warehouse through an extract transform load process. It's called an ETL, the acronym, where the data were copied from various sources, cleaned, reshaped into a certain structure, and then stored in the data warehouse for using, for instance. In other words, data needed severe cleaning and pre-processing in order to be utilized. To reach this data, users needed to write ad hoc queries, or there were some dashboards or reports, some made from the IT experts dashboards, ready-made, ad hoc made, which were frequently requested by users, so they could access those data. So here we see the pipeline where the raw data are stored through the ETL process described before. So it was the extract, transformation, and load into the data warehouse. And the end user, the various end users, query or get data through reports, dashboards, etc. Now, with regards to the tools, the third aspect of the strategy, data warehouses implemented some new technologies relative to the traditional relational database models. The data warehouse separates data into fact tables, where measurements were stored, and dimension tables, which contained descriptive attributes. The users could interact with the data via reporting software, as we saw before, to view the static data, summaries, etc. In a more sophisticated architecture, analysts could take advantage of online analytical processes, the OLAP cubes. Usually they rely on star schema and let users to query the data across dimensions through interactive sessions. By this point, end users had some autonomy in how they looked and acted upon the data. Also, automated processes to inform business activities through data were also put in place. Alerts probably trigger a certain alert when a threshold of an attribute drop below a certain number, let's say. Basic what-if analysis also helped users to evaluate decisions and plan for the future. But given the limited sources of data from the data warehouse, because they were not actually able to directly communicate with those data, there were limited ways to customize and work with the data. While reporting and basic analytics were automated, end users operated largely without the assistance of models developed by the statisticians. Also, business intelligence and operations research seek to create values from data. Now, with regards to the fourth aspect, the data themselves. During this period, the early period of analytics, data tended to be transactional, mostly, and combined into tables, stored into relational databases. that were ultimately processed into a data warehouse. Under this process, data was gathered from specified sources at specific times, let's say, and sometimes not even all of the data made its way to come to the warehouse. Some of them it was just as unimportant, so they were not stored at all. So what we have seen so far with these platforms, the first versions, let's say, of analytic platforms, is that the relative rigid nature of the data warehouse made changes to the collection and dissemination of the data was difficult. Subsequently, business agility was limited to take knowledge from those data. Users could get historic data about the business through static report to get knowledge about this from this data. It was the early stage of the descriptive analytics. It's what we have in our data, kind of. What is the information in there? This could be retrieved. Through the OLAP tubes, they could possibly even dig into the data to parse out cause and effect. It was a diagnostic analytics, let's say. But when there was no immediate access to broader data, it was difficult to advance to predict, let's say, some certain features. So predictive analytics were limited. Kind of, you could not ask to a system, okay, what is going to happen in the future? You could not forecast. You needed the expert guys, the statisticians, or the data scientists. But by then, I think data science didn't exist as a profession, let's say. Now, about the present, how nowadays this analytics work, platform work. Starting in the late 2000s, it was by the beginning of the big data era, and the famous 3 V's of big data. It was about the volume of data, the velocity, the speed of how quickly they move from the one source to the other, and the variety, the multidimensionality of the data. New approaches of utilizing analytics has been arised since then. And it was then that the diagnostic analytics came in front, and the capability to answer why did it happen started to take place. So let's see again with regards to these 4 aspects of the key elements of the strategy of analytics. So by the time the big data emerged, the role of the data scientists also emerged. This guy blends quantitative and domain expertise with a greater degree of computational thinking. These skills became necessary both to handle the greater variety and volume of data sources and to update and deploy data and analytics models without the assistance of IT professionals. So some kind data scientists came in front and they were able to run those predictive models and without the need of ITs to make queries, etc. in the databases. IT professionals no longer need to always clean the data before collecting them, this ETL process that we mentioned before. And now these teams could focus on ease of use and speed to govern access in the databases. With these new workflows and structures in place, domain leaders are better able to manage with data. So through self-services of business intelligence tools, and from frequent collaboration with data scientists and other data specialists. With regard to the processes now, IT professionals now seek to collect data as is from any possible source of value. This data can be in a variety of formats, so few predefined rules or relationships are established for ingestion. They can take all each kind of data they have and store them without the need to clean them, to transform them, etc. This is done by the data scientists who have the data insights and know what to do with them and how to deal with them, to manage them. Depending on the data size, the data is processed in batch over discrete time periods or in stream and events near real time. In case we have big data and real-time data, this is how it works. Because the data cleaning is the last step, this process, the process that we described before, the ETL, is now referred to as an extract, load, transform process, rather than extract, transform, and load to the database process in the previous architectures. So for the data scientists, faster access to more and dynamic data enables the development of training sets of data for machine learning models. The ELT processes allow the development of machine learning model. The model performance is improved the more data we pass through them. We train the model and we have an increase to the model performance. As more data is collected, the importance of the data governance process typically grows, describing who has authority over the data and how the data should be used. Kind of policies of data management has to be taken into account. Similar approaches are necessary to audit how models are put into production and how they work. Now, with regard to the tools, it is understandable that the tools also has to be changed now. It's not the same databases that we are going to store our data. The previous one, it was a relational databases where the data should be pre-cleaned, transformed, etc. before stored into the data. Now, that was difficult. And the approach now is like the data lakes, let's say. It is a repository of data stored in its natural raw format, introduced to cope with the problem of those big data came up. The data lake is often powered by cloud computing for the benefits of reliability, redundancy, and scalability. Dominant cloud service providers like Amazon Web Services, Microsoft Azure, Google Cloud Platform, and open source technologies like Hadoop or Spark, used to process big data, utilize those kind of data stores. The difference between those two data stores, the data warehouse, the traditional databases, let's say, and the data lakes, it's the data in the first one, the data is processed and organized into a single schema before being put in the warehouse. We have the raw data. As we said before, there has to be this process, ETL process, extract, to take the data from the source, to transform it and load it to the database. Here, structure, you see, the columns, etc. It has to have a clear structure. And then the analysis on those data is taking place on the cleaned data of the warehouse. While in the data lakes, the raw and unstructured data goes directly into a data lake, into a database, let's say. And then the data is selected and organized as and when needed. So it is the job of the data scientist to see which data he needs for his analysis, for his models, their models, and utilize them accordingly. You can understand that the one approach doesn't replace, substitute the other. They could exist simultaneously in a system, like the one that we have here in the Holy Aedicule platform. Depends on your data. If you have a lot of data, unstructured data, rather than spending hours, days, probably, or months to clean them and put them in structure, and then you will not be able to access them because this kind of accessing relational, traditional databases, let's say, having big data it's an approach that is not used. You use both. If you have big data, you use data lakes, let's say. While if you don't have, if you have some data sources that it's not considered as big data, tables, let's say, you can use the other, the data warehouse, the traditional database. Both are utilized in our platform, depending on the data we have. As we said, it's a multidimensional data, the one that we have available, so we use both. So, in the big data, the data is mostly unstructured. And as I said before, they are stored in non-relational database systems. By increasing the volume, the velocity, and the veracity of the data, and the use of data lakes along with the data warehouses, enable the data-driven decision. That was not possible in the early stage, the past platforms. They could not support the data-driven decisions. Need for better ways to scale arise and share business intelligence. Through interactive, immersive exploration and visualization of the data, like making visual reports, dashboards. So this is some software, some applications utilized for these purposes. Spotfire, Jaspersoft, etc. And business intelligence tools have been matured, and they provide self-service capabilities and automations for end users, which also have matured. So someone can utilize those. The analytics pipeline now here, as we said before, we have different, the various data sources, let's say. We have the data acquisition, depending on where we want, what is the type of data we have retrieved and we want to store. We store them even in a data warehouse or in a data lake. Then the analysis, visualization, whatever you need is taking place. And the end user grasps whatever he needs. Here, the end user is the data scientist, let's say, a kind of expert. Now, with regards to the data, the fourth key element of the strategy, contemporary analytics expands the variety of data available. So we have structured tables and unstructured sources like natural language and images are available. And on account of streaming processes, so real data that coming all of the time, refreshes of this data are available in minutes or even less. With this, the batch process approach. The data lake can accommodate real-time events such as Internet of Things sensors, readings, GPS signals, etc. Now, to summarize what we have seen in nowadays, what the analytic platforms do is they can give us data-driven insight into the hands of end users quickly, with technology allowing them to interact with it on a deeper level. Data scientists build machine learning models that improve with more data. You can very easily, using drag and drop tools, to set up processes and analyze data without technical assistance, let's say. The cloud automation and streaming technologies enable easier adoption and planning for changing circumstances. Machine learning works only so long in production before the algorithm struggles to account for changes to the business and needs intervention. The data scientists undertake those predictive challenges. And business intelligence professionals and domain experts tend to operate solely in analyzing current or past data. The only problem, let's say, not problem, the only thing that is not very well covered with these platforms is that there is a need for greater and easier collaboration among the data scientists, the business intelligence experts, the analytic teams, the end users, and the consumers of analytic insights. This is the gap that our platform is coming to cover, to fill, through using converged analytics, unifying advances in artificial intelligence, streaming data, and relating technologies into seamless analytics experience for all users, making able, unlocking the one aspect, the prescriptive analytics, the one that was not able to be done so far. So in order to be able to allow the model, to enable the model, tell us what to do to make a decision. Not only what is happening and what is going to happen, the predictive, the descriptive and the predictive analytics, but also the prescriptive analytics, how we're going to do something. Utilize the information came up from the data. Now let's see again through those four aspects of the strategy, how this is how this concerns each one of them. The end users here are in the center. Their decision making is augmented by automation. Teams can work cross-functionally and in parallel across different domains, iterating the system to their needs, with the raw time and human resources needed to create and maintain analytic products, such as dashboard models, predictive models, etc. And resulting in more collaboration, more automation, and greater scale for data-driven insight as a result of the convergence of teams and work streams. With regards to the processes, the ends of older analytic approaches remain the same. The means, let's say, change, but the ends is the same. So insights, whether historic or in support of future decisions, using governed data and processes, given the volume, the velocity, and the veracity of data, centralized approaches are less than optimal. An integrated architecture offers a smart approach for providing the right insights at the right time to users of all technical levels, not only to the data scientists or to the IT experts in the two previous, let's say, versions. And the ability to deploy quickly and adjust the data products, let's say, optimize production, bring more machine learning models into production, to have more predictive analytics faster and at scale, in case you have big data. To do this, the practice of model OPS is used to institute and govern those raised needs. This is about collecting and update. This is depicted in this cycle here. Firstly, collect and update the data from a business problem, whatever problem we have. Prepare and refine the data. Use algorithms to train a model to solve business problems. Put the model into production, monitor the model to measure effectiveness and test for drift or bias. Retrain the model to improve performance. And again, the same, the vicious cycle. So with regards to the data, a primary feature of converged analytics is the blending of historic and real-time data. IoT sensors readings, as mentioned before, GPS signals are available for intermediate analysis and modeling, and utilize of streaming data Utilization of streaming data combined with already acquired data, like the ones we have from the rehabilitation project, can be used to drive continuous model deployment and prediction. Now, with regard to the tools, the backend provisioning is no longer served by those monolithic, let's say, the first systems that I described in the beginning, but rather by composable groups of microservices. This arrangement supports elastic and scalable analytics. Composability makes it easier to adapt to changes driven in part by a growing volume and variety of data sources. So now users no longer need to wait for a data scientist to provide deeper insights, ad hoc deeper insights. They have all the data-driven insights at their fingertips, let's say, assisted by artificial intelligence to quickly explore and make decisions. Now, with regards to the data management and the particular system that we have developed to a certain extent, it is an interdisciplinary scientific tools where there are optimized spatial databases and different kind of databases in order to deal with or to manage all of these different type of data. Serve needs with respect to the data storage and data querying. Allow spatial data registration and enable the spatial data querying through visualizations. So the researchers from different disciplines can register their data directly to the system by selecting a location and area where the measurement was made. So digitally driven design is achieved through prescriptive analytics to support decision making for the cultural heritage assets. It is a multi-layer data management and big data integration. We have different types of data: non-destructive testing data, analytical technique data. Mostly they are kind of tabular data, while the non-destructive tested data are images, unstructured data, spatial data, time, etc. The platform architecture is presented here on the right side of the screen. The different data sources, the text, we have text, images, tables, etc. They are integrated into data models stored in the respective appropriate database, data store. And through those data models, depends on if it is a geometric coming from the geometric documentation, historic documentation, architecture, etc. Certain machine learning algorithms and models have been developed to analyze this data and have not only prediction models but also prescription models to suggest you, to give you suggestions of what to do in certain cases. Also, the ability to take to utilize data from various data sources like streaming data, as mentioned before, is also accounted. Then the cultural heritage analytic results are presented through a visualization, including 3D representation, and this architecture is the initial architecture, the one that we have come up for the first state of the project, and it's going to be updated, including also policy aspects, etc. Some snapshots of this platform. Here we have the 3D model of the Holy Aedicule. We said that it's a transdiscipline data analytic approach. We have spatial time, content data, different content data. We can search data and metadata. It's modular, extendable, and transferable. You can use it in every computer, set it up in every computer. There is multi-layer, multi-phase information stored there for all of the construction phases, rehabilitation phases. and all of the data that have stored are georeferenced. So you can choose a certain location, an area on the model, and store the data to this particular area where the measurement was made. Also, you can walk through navigation. You can play with this model and see different aspects. You can make sections in all axes, X, Y, Z, in all planes. And here we can see the, let's say, multi-layer data fusion. We have infrared thermography, campaign of infrared thermography measurement has been made. So all of this information can be visualized on the texture of the 3D model. You can, as you can see here, you can add data on certain areas, retrieve data from certain areas. You can filter data, pre-process data. As presented in the previous, I forgot to mention this. So here, this is the stage where data pre-processing takes place. Before storing the data in the data store. And finally, the usability of the purpose is to have the usability of the digital-driven preservation of cultural heritage, where from fragmented usability, where user take into account user requirements, fragmented knowledge from all of these disciplines, and also take into account land use and urban planning, socioeconomic development, multicultural dialogue and tolerance, have a holistic digital-driven infrastructure, and that will lead to holistic usability of the platform, of the system. That's all. If you have any question. Can you hear me? Can you hear me? No? All of this time I was talking to.
Only Akuyes, we can hear you.
Okay, thank you.
In the chat, there is a message from Chiara.
Let me check. Yes, I see now. Okay, if you don't have any other question, thank you very much.
So I wish to thank the PhD candidate Manolis Alexakis for his presentation. I hope it was presented in an educative way so that whoever would understand how we develop and function the platform's analytics in order to manage in a multi-layer way our data.